the differential forms of the fundamental laws. Before we go for tutorial number 1, I would like to advise you that there is a few rule of thumb that you need to understand to make the solution for this topic easier. First, you need to remember the continuity equation and Navier-Stokes equation very well. Then try to make a good and correct assumption for that question. So with that assumption here, we could simplify the equation. Then for sure, I think to solve this problem you need to integrate, or sometimes you need to do the differential solution to solve your problem. So make sure that you could solve integration and differential problems very well. So this is the tutorial number 1. The question is, simplify the x component Navier-Stokes equation for steady flow in a horizontal rectangular channel, assuming all streamlines are parallel to the wall. Let the x direction be in the direction of flow. So this is the diagram given for this tutorial. So we need to imagine that we have a rectangular channel like this, and then we have an x-axis here, and this is the z-axis, and this is the z-axis, and this is the y-axis. And then from the side view here, the velocity profile will look like this, and from the top view here, mean the width of this channel is b, and the velocity profile will show like this. Because we are solving problem with a velocity with movement of fluids, so we need to use the Navier-Stokes equation. And from the question, we know that the water or the fluid is flow from in x direction, so it is better for us to use the x direction for Navier-Stokes equation. From notes, we know that a part of Navier-Stokes equation will have this term. And for incompressible flow, a flow in which the density of a fluid particle does not change as it travels along, we found that du over dt is equal to 0. So it is because du dt is equal to 0 because it is a steady flow. Velocity do not change with time. Du dx is also equal to 0 because it is a uniform flow. Velocity not change with location. And then because in the question it discuss only for x direction, so means the velocity for v and w is equal to 0. There are no velocity in y and z direction. So this is the simple form of momentum equation or Navier-Stokes equation. So we have rho dv over dt is equal rho gx minus nabla p plus mu nabla square v. So because we are only discussing about x direction, we could change v here into u. It is to simplify our calculation here. So we change everything here with u, and then we make an assumption to simplify our equation. We could say that du dt is equal to 0 because it is in steady flow. So you may refer our previous discussion in this video. We also have rho gx equal to 0 because the gravity only acts in vertical direction, not in x direction. So this is the full term for nabla p, nabla pressure. So it is equal to del p over del x plus del p over del y plus del p over del z. And because we have no motion along y and z direction, so we could say that del p over del y here is equal to 0, and del p over del z is also equal to 0. we could take the value of delta of nabla p here is equal to del p over del x. And this is the full term for nabla square u. You could see these terms here. And at this question, we could take that del square u over del x square is equal to 0 because the flow is uniform and there is no velocity change at any point. You may also refer this term into this diagram. For example, if we see this is the side view of the velocity profile here, so we could find that this is the x-axis. So we found that yes, the velocity profile is in curve profile like this, but we could say that at any point here, the velocity is steady, so the du dx del u over del x is equal to 0. There are no changes of velocity along the x direction. However, for del u over del y, for example, if we see in y-axis here, we could say that we could find that the velocity will change along the y direction, because we could say that at lower point here the velocity is lower compared to the middle point here, and the velocity is become smaller again towards the end of this flow. So the value of du dy is not equal to 0. And also if we look at the top view here, we could say that the velocity over z, this is the z direction, so the velocity toward the z direction is changes at the beginning here and also change at the end here. So the du dz is not equal to 0. So we take du dy, du dx here is equal to 0. So we could simplify nabla square u is del square u over del y square plus del square u over del z square. And then we combine all the answer, we could get this expression. So this is the simple Navier-Stokes equation. We substitute all the finding, all the answer for each term here. So we could get 0 is equal to 0 minus del p over del x plus mu del square u over del y square plus del square u over del z square. And then we could bring it to just hidden the value of negative here, so we bring the del p over del x to the left side, so we have get the expression for pressure over the x direction as given here.